G'day again. Welcome back to Mathematics 302. Hope you're having a good morning or good evening, as the case may be. This is lecture 11. I'm just going to move my picture down here, and this is part C, so the final part of lecture 11. So we're going to do separation axioms, product spaces, which you've probably seen before in second year, connectedness, complete metric spaces, and function spaces of R. So some of this will overlap in different lectures that we have in this subject. Okay, so let's go. Separation axioms. So a set of conditions for a topology that describes how well open sets can distinguish between points or separate subsets. So that's what a separation axiom is. Now there's a hierarchy of properties, which are like T0, T1, T2, etc., etc. And each subsequent axiom represents a stronger form of separation. So the best way I've thought of, and you might think of a better way, to compare these sorts of things is where you're splitting things up by stricter and stricter conditions, so that if you can't be one and be the other, you can't be a T0 and be a T1. Once you're a T1, you're no longer a T0, although you can satisfy some of the properties of that. The best thought I had was actually in gaming. So in computer gaming, when you're like on level 0 or level 1, once you get through to level 1, well, in some games you can go back to being in level 0, but in other games, you're into level 1 and that's it. That's your next move. So I was just thinking of levels in gaming as being things where a mathematician or a computer programmer would use something like a separation axiom where a person would pass through sorts of things. So anyway, that's something to keep in mind for your logic. And if you thought you want to be a programmer to create games, you'll probably use these sorts of things in the background, but you might not know what they're called. So here we go. So these are the separation axioms. So Kolmogorov, for any two distinct points, there's an open set containing one but not the other. And we get more stricter with Frechet. For any two distinct points, there's an open set containing the first point but not the second, and another open set containing the second but not the first. Holstorff, for any two distinct points, there are two disjoint open sets, one containing each point. A regular, now this is where you start smiling and possibly laughing at the names that they've given them from T3 onwards. A space that satisfies T1, and if a point is not in a closed set, there are two disjoint open sets, one containing the point and the other containing the closed set. Normal. Now, what's the difference between regular and normal? Bit of bit of language there. That's about it. For any two disjoint closed sets, there are two disjoint open sets, one containing each closed set. Now get this, completely normal. Okay, you start laughing a little bit. It's a T4 space that's also hereditary. Every subspace is normal. And then get this one, perfectly normal. A space where, I think my image is a little bit in the way there. A space where any two disjoint closed sets are perfectly separated by a continuous function into 0, 1. So there you go, got regular, normal, completely normal, and perfectly normal, not to be outdone. So they're the separation axioms of points between where you've got two different sets. Okay, example questions. So these are just two simple example questions. What's the topological difference between a Kolmogorov space and a Hausdorff space? And that's pretty simple, as long as you've studied what the different axioms are. The main difference is while Kolmogorov, and you might not write it in these words, while Kolmogorov space ensures at least one point has a unique neighborhood, or Hausdorff space requires that both points have disjoint neighborhoods, open neighborhoods. And second question, can a Kolmogorov space be non-Frechet? Well, be non-Frechet, there we go. Yes. For example, a space with 2 points and a single open set is Kolmogorov, but not Frechet, since there's no open set that contains 1 point without the other. Okay, so they're just some simple, simple questions. And it's really just a logic difference of if you've ever done like logic, yes, no, off, on, not, sorts of things, and, or. There's really the difference here in separation axioms. Product spaces. Now, hopefully by this year, which is third year, you would have seen a product space before. So this hopefully is just a revision. A product space is a Cartesian product of a topological space. And I'll just give you a few simple examples. Determine the Cartesian product for A equals 1, 2, and B equals x, y. Well, it's very, very simple. AB is 1x, 1y, and 2x, 2y. So you've got this new set, which is the Cartesian product of it. Determine the Cartesian product for A, 1, 2, 3, and B, 5, 6. We're just doing the same thing. 1, 5, 1, 6, 2, 5, 2, 6, 3, 5, 3, 6. When you do a Cartesian product, whatever's mentioned first is first. So here, I've used different numbers so you're not getting confused. So here you've got the 1 and the 2 first. So whatever set is mentioned first, and then you've got and the other one, it always stays in that order. So you don't want to reverse that because you're producing a different Cartesian product. Okay, pretty simple. Connectedness, and again, you hopefully would have seen this in other lectures within this course and possibly other subjects. A topological space is considered to be connected if it cannot be split into two or more empty subset. Connected example, the closed interval of real numbers cannot be split into two subsets since it is not possible, and I've made up this, to determine the next real from any cut point. So I've just made up this. For example, for 0 to 0.5 and B from R to 1, it's not possible to determine the real number R. So you can't exactly split, and here we're just using from 0 to 1. You can't split any set of real numbers in between. You can't find the next one. So you could take a real number out. So if I took out 0.5 and you went from 0 to the thing before 0.5 and then from the thing after 0.5, you could do that. But good luck finding the actual number that's the next number after 0.5. You could determine it with an open set, but you can't actually split the interval and go, okay, I'm going from 0.5 to what's the next number again? You can't actually figure that out in the set of reals. Here's a disconnected example. In this set, you can. The set of rational numbers from 0 to 3, a set of integers would be even easier, can be split into two subsets around root 2, since you can calculate a different rational number on either side. So, for example, from 0 to x and B from y, A is 0x and B is y3, where x and y are either side of root 2. So therefore, in the rational numbers, there's gaps. In the real numbers, there's no gaps. So where you've got rational numbers, integers, that sorts of things, you can split those into subsets because there are gaps. So you can say, okay, well, we'll stop here, and here we're picking an irrational number. So there's going to be a rational number on this side, and a rational number on that side, so you can split it. So there you go. Pretty straightforward, really. Okay, complete metric spaces. A complete metric space, and we've spoken about metric spaces in other lectures. A complete metric space is one where every Cauchy sequence converges to a limit that's also within the space. For example, is the closed set a complete metric space? So it's a closed set using those square brackets. Yes, since it's closed and therefore connected and includes the endpoints, making it complete. Is the Clopen set 1, 2, 3 a complete metric space? And the answer is obviously no, since it's not connected, does not contain its endpoints, which means, or does not contain this endpoint at 1, which means it converges to a point outside the space. So it can't be complete if it does do that. Last one, function spaces of R. Function spaces of R are defined as a set or a collection of functions, so not just a single one, that have the same domain and codomain. Okay, example questions. Are the functions fx equals sine x and fx equals cos x linearly independent because they're in the same function space, which is in R2? Yes, since sine x and cos x cannot be expressed as scalar multiples of each other, the only solution for a sine x equals b sine x is when a and b are 0. So that's just a question you could ask within a function space. It's not a question about the function space. It's just a question within a function space. How can the reals and the xy plane be related as function spaces? So they're not the same function space, they're just related. So answer, ordered pairs of reals can be used to relate the real one-dimensional space to the two-dimensional xy plane. So just very simple questions there, and just some notes. A single function which maps from R to R2, so let's suppose you're mapping a circle to the outer rim of a sphere, and that's a good map. That's not a function space. Okay, a function space is a set of functions. So if you map every single circle in R to every single rim of every single sphere in R2, that will be considered a function space. Another example would be the set of all vectors in R3 could be considered a function space. Okay, that's it. God bless you. Stay safe. I'll see you next week uh, in week 12, which will be revision for assessment 3. So God bless you. I'll see you. Bye.